In computer science, future, promise, and delay refer to constructs used for synchronization in some concurrent programming languages. They describe an object that acts as a proxy for a result that is initially unknown, usually because the computation of its value is yet incomplete. The term promise was proposed in 1976 by Daniel P. Friedman and David Wise, and Peter Hibbard called it eventual. A somewhat similar concept, future, was introduced in 1977 in a paper by Henry Baker and Carl Hewitt. Specifically, when usage is distinguished, a future is a read-only placeholder view of a variable, while a promise is a writable, single assignment container, which sets the value of the future. Notably, a future may be defined without specifying which specific promise will set its value, and different possible promises may set the value of a given future, though this can be done only once for a given future. In other cases, a future and a promise are created together and associated with each other. The future is the value, the promise is the function that sets the value, essentially the return value of an asynchronous function. Setting the value of a future is also called resolving, fulfilling, or binding it. Applications. Futures and promises originated in functional programming and related paradigms to decouple a value from how it was computed, allowing the computation to be done more flexibly, notably by parallelizing it. It later found use in distributed computing, in reducing the latency from communication round trips. More recently, it has gained popularity by allowing writing asynchronous programs in direct style, rather than in continuation passing style. Implicit versus explicit. Use of futures may be implicit or explicit. Obtaining the value of an explicit future can be called stinging or forcing. Explicit futures can be implemented as a library, whereas implicit futures are usually implemented as part of the language. The original Baker and Hewitt paper described implicit futures, which are naturally supported in the actor model of computation and pure object-oriented programming languages like Smalltalk. The Friedman and Wise paper described only explicit futures, probably reflecting the difficulty of efficiently implementing implicit futures on stock hardware. The difficulty is that stock hardware does not deal with futures for primitive data types like integers. For example, an add instruction does not know how to deal with 3 plus future factorial. In pure object or actor languages, this problem can be solved by sending future factorial the message plus 3, which asks the future to add 3 to itself and return the result. Note that the message passing approach works regardless of when factorial finishes computation and that no stinging, forcing is needed. Promise pipelining. The use of futures can dramatically reduce latency in distributed systems. For instance, futures enable promise pipelining, as implemented in the languages E and Joule, which was also called call stream in the language Argus. Consider an expression involving conventional remote procedure calls, such as T3 equals C, which could be expanded to T1 equals X, A, T3 equals T1, C. Each statement needs a message to be sent and a reply received before the next statement can proceed. Suppose, for example, that X, Y, T1, and T2 are all located on the same remote machine. In this case, 2 complete networked round trips to that machine must take place before the third statement can begin to execute. The third statement will then cause yet another round trip to the same remote machine. Using futures, the above expression could be written T3 equals less than C, which could be expanded to T1 equals X less than A, T3 equals T1 less than C. The syntax used here is that of the language E, where X less than are asynchronously to X. All 3 variables are immediately assigned futures for their results, and execution proceeds to subsequent statements. Later attempts to resolve the value of T3 may cause a delay, however, pipelining can reduce the number of round trips needed. If, as in the previous example, X, Y, T1, and T2 are all located on the same remote machine, a pipelined implementation can compute T3 with one round trip instead of 3. Because all three messages are destined for objects which are on the same remote machine, only one request need be sent and only one response need be received containing the result. Note also that the send T1 less than C would not block even if T1 and T2 were on different machines to each other, or to X or Y. Promise pipelining should be distinguished from parallel asynchronous message passing. In a system supporting parallel message passing but not pipelining, the message sends X less than or in the above example could proceed in parallel, but the send of T1 less than C would have to wait until both T1 and T2 had been received, even when X, Y, T1, and T2 are on the same remote machine. The relative latency advantage of pipelining becomes even greater in more complicated situations involving many messages. Promise pipelining also should not be confused with pipelined message processing in actor systems, where it is possible for an actor to specify and begin executing a behavior for the next message before having completed processing of the current message. Read-only views. In some programming languages such as Oz, E, and Ambient Talk, it is possible to obtain a read-only view of a future, which allows reading its value when resolved, but does not permit resolving it. In Oz, the operator is used to obtain a read-only view. In E and Ambient Talk, a future is represented by a pair of values called a promise, resolver pair. The promise represents the read-only view, and the resolver is needed in order to set the future's value. In C++ 11 or STD, future provides a read-only view. The value is set directly by using a std promise, or set to the result of a function call using std packaged underscore task or std async. In the Dojo Toolkit's deferred API as a version 1.5, a consumer-only promise object represents a read-only view. In Alice ML, futures only provide a read-only view, whereas a promise contains both a future and the ability to resolve the future. In Net 4.0 system, threading, tasks, task less than T greater than represents a read-only view. Resolving the value can be done through system, threading, tasks, task completion and source less than T greater than. Support for read-only views is consistent with the principle of least authority, since it enables the ability to set the value to be restricted to subjects that need to set it. In a system that also supports pipelining, the sender of an asynchronous message receives the read-only promise for the result, and the target of the message receives the resolver. Thread-specific futures. Some languages, such as Alice ML, define futures that are associated with a specific thread that computes the future's value. This computation may be started either eagerly when the future is created, or lazily when its value is first needed. A lazy future is similar to a thunk. Alice ML also supports futures that can be resolved by any thread, and calls these promises. Note that this usage of promise is different from its usage in E as described above. An Alice promise is not a read-only view, and Alice also does not support pipelining for promises themselves. Instead, pipelining naturally happens for futures. Blocking versus non-blocking semantics. If the value of a future is accessed asynchronously, for example by sending a message to it, or by explicitly waiting for it using a construct such as when in E, then there is no difficulty in delaying until the future is resolved before the message can be received or the wait completes. This is the only case to be considered in purely asynchronous systems such as pure actor languages. However, in some systems it may also be possible to attempt to immediately or synchronously access a future's value. Then there is a design choice to be made. The access could block the current thread or process until the future is resolved. This is the semantics of data flow variables in the language Oz. The attempted synchronous access could always signal an error, for example throwing an exception. This is the semantics of remote promises in E. Potentially, the access could succeed if the future is already resolved, but signal an error if it is not. This would have the disadvantage of introducing non-determinism and the potential for race conditions, and does not appear to be a common design choice. As an example of the first possibility, in C++11, a thread that needs the value of a future can block until it is available by calling the wait member functions. You can also specify a timeout on the wait using the wait underscore for member functions to avoid indefinite blocking. If the future arose from a call to std async, then a blocking wait may cause synchronous invocation of the function to compute the result on the waiting thread. Related constructs. An IVAR is a future with blocking semantics as defined above. An I structure is a data structure containing IVARs. A related synchronization construct that can be set multiple times with different values is called an MVAR. MVARs support atomic operations to take or put the current value, where taking the value also sets the MVAR back to its initial empty state. A concurrent logic variable is similar to a future, but is updated by unification, in the same way as logic variables in logic programming. Thus it can be bound more than once to unifiable values. The data flow variables of OS act as concurrent logic variables, and also have blocking semantics as mentioned above. A concurrent constraint variable is a generalization of concurrent logic variables to support constraint logic programming. The constraint may be narrowed multiple times, indicating smaller sets of possible values. Typically, there is a way to specify a thunk that should be run whenever the constraint is narrowed further. This is necessary to support constraint propagation. Relations between the expressiveness of different forms of future. Eager thread-specific futures can be straightforwardly implemented in terms of non-thread-specific futures, by creating a thread to calculate the value at the same time as creating the future. In this case, it is desirable to return a read-only view to the client, so that only the newly created thread is able to resolve this future. To implement implicit lazy thread-specific futures in terms in non-thread-specific futures, needs a mechanism to determine when the future's value is first needed. If all values are objects, then the ability to implement transparent forwarding objects is sufficient. Since the first message sent to the forwarder indicates that the future's value is needed, non-thread-specific futures can be implemented in terms of thread-specific futures, assuming that the system supports message passing, by having the resolving thread send a message to the future's own thread. However, this could be argued to be unnecessary complexity. In programming languages based on threads, the most expressive approach appears to be to provide a combination of non-thread-specific futures, read-only views, and either a wait-needed construct or support for transparent forwarding. Evaluation strategy. The evaluation strategy of futures, which may be termed call by future, is non-deterministic. The value of a future will be evaluated at some time between when the future is created and when its value is used, but the precise time is not determined beforehand and can change from run to run. The computation may be started as soon as the future is created or only when the value is actually needed, and may be suspended part-way through or executed in one run. Once the value of a future is assigned, it is not recomputed on future accesses. This is like the memoization used in call by need. A lazy future is a future that deterministically has lazy evaluation semantics. The computation of the future's value starts when the value is first needed, as in call by need. Lazy futures are of use in languages whose evaluation strategy is by default not lazy. For example, in C++11 such lazy futures can be created by passing the std launch deferred launch policy to std async, along with the function to compute the value. Semantics of futures in the actor model. In the actor model, an expression of the form future less than expression greater than is defined by how it responds to an eval message with environment E and customer C as follows. The future expression responds to the eval message by sending the customer C a newly created actor F as a return value concurrently with sending less than expression greater than an eval message with environment E and customer C. The default behavior of F is as follows. When F receives a request R, then it checks to see if it has already received a response from evaluating less than expression greater than proceeding as follows. If it already has a response V, then if V is a return value, then it is sent the request R. If V is an exception, then it is thrown to the customer of the request R. If it does not already have a response, then R is stored in the queue of requests inside the F. When F receives the response V from evaluating less than expression greater than, then V is stored in F, and if V is a return value, then all of the queued requests are sent to V. If V is an exception, then it is thrown to the customer of each of the queued requests. However, some futures can deal with requests in special ways to provide greater parallelism. For example, the expression 1 plus future factorial can create a new future that will behave like the number 1 plus factorial. This trick does not always work. For example, the following conditional expression. If m greater than future factorial, then print, else print suspends until the future for factorial has responded to the request asking if m is greater than itself. History. The future and or promise constructs were first implemented in programming languages such as Multilisp and Act 1. The use of logic variables for communication in concurrent logic programming languages was quite similar to futures. These started with Prolog with freeze and IC Prolog, and became a true concurrency primitive with relational language concurrent Prolog, guarded horn clauses, Parlage, Strand, Vulkan, Janus, Mozart, Oz, Flow Java, and Alice ML. The single assignment IVAR from dataflow programming languages, originating in Hedon included in Ruppy's concurrent ML, is much like the concurrent logic variable. The promise pipelining technique was invented by Barbara Liskov and Luba Schreier in 1988, and independently by Mark S. Miller, Dean Tribble and Rob Gillinghouse in the context of Project Xanadu circa 1989. The term promise was coined by Liskov and Schreier, although they referred to the pipelining mechanism by the name call stream, which is now rarely used. Both the design described in Liskov and Schreier's paper, and the implementation of promise pipelining in Xanadu, had the limitation that promise values were not first class. An argument to, or the value returned by a call or send could not directly be a promise. It appears that promises and call streams were never implemented in any public release of Argus. Argus development stopped around 1988. The Xanadu implementation of promise pipelining only became publicly available with the release of the source code for Irudanax Gold in 1999, and was never explained in any published document. The later implementations in Dual and E support fully first-class promises and resolvers. Several early actor languages, including the ACT series of languages, supported both parallel message passing and pipelined message processing, but not promise pipelining. More recently, there has been a major revival of interest in futures and promises, due particularly to their use in responsiveness of user interfaces, and their use in web development, due to the request-response model of message passing. Several mainstream languages now have language support for futures and promises, most notably popularized by the async and await constructions in .NET 4.5, largely inspired by the asynchronous workflows of fhash, which dates to 2007. This has subsequently been adopted by other languages, notably Dart, Python, Hack, and drafts of ECMAScript 7, Scala, and C++.